I'm Eric Marshiner. I'm a verification architect at Mentor Graphics, and I'm presenting a poster today on successive refinement, which is a methodology that has been developed by ARM and incorporated into the UPF specification for 2.0 and is being elaborated further in UPF 3.0. This methodology is described here in this picture here, and it involves successive development of UPF, starting with IP creation, IP configuration, and then finally the implementation of the system. This complements the original UPF flow, which was implementation oriented, and that's shown here on the right-hand side, where UPF is added to RTL and then run through the implementation process and verified along the way. In a successive refinement flow, the issue is how that UPF gets developed initially, and the development involves starting with UPF constraints applied to the IP and then configuration of a system for the specification of the logical management of power using those IP constraints, finally getting to implementation. And this flow has a number of advantages. First of all, it allows the IP provider to guide users of the IP in the correct application of that IP in a power managed system. In addition, the specification of the configuration, which is a logical configuration, allows the system to be verified prior to implementation details, which makes it easier to verify, which makes it easier to separate the logical aspects from the physical implementation aspects, and ultimately makes verification go better and allows it to start earlier in the process. So this IP constraint UPF is illustrated here. Here is an IP ARM Cortex MP Core processor IP, which has been for which constraint UPF has been written, and that constraint UPF consists of the following kinds of commands. It defines the power domains that are used in the IP, and these are atomic power domains, which is to say that the user is not allowed to further partition them because the IP won't work correctly if they're partitioned further. It also defines retention constraints and isolation constraints, which tell the user what they must retain or must isolate if they choose to power down parts of the IP in a given system application. Finally, it defines power states, and these include both fundamental power states and also potentially abstract power states that are used to specify constraints on power states. All of this is defined by the IP provider, and of course it's defined in the absence of any knowledge of how the IP will actually be used. So this is all conditional, and then these conditional constraints are imported into the configuration of the system that the user is building. In that case, for example, up here where the Cortex MP Core processor IP has been incorporated into a larger system, in the gray box, one of the things the user has to do is control power for this larger box. And that includes providing the control logic that will be necessary to apply retention or apply isolation when power is being removed from certain portions of the design. And that's defined here. There's control logic signals, retention strategies, isolation strategies, and these are all based on what the user has decided to actually implement in the implementation of this design. In addition, the power states that are defined for the system are updated with the control signals, so simulation can proceed in a way that reflects the control of the system at this level. Later on, when the implementation is done, all of this information is then pulled into the into the implementation UPF file and extended with implementation dependent information. This is information about construction of the supply network and distribution of power to the different power domains in the entire system, as well as technology specific information about which libraries to use, which cells to use in the libraries, locations of isolation cells, and other related issues. So here we have, for example, creation of the supply network elements, the supply ports and nets, creation of power switches, updating supply sets with supply nets, that's connecting the supply distribution to the power domain supplies, and then adding voltage information, which is now evident because we've made technology decisions. And then some other technology-specific information may also be provided. This partitioning into constraints, configuration, and implementation not only helps the user ensure that he's using the IP correctly when he integrates it into a system, but also allows him to validate the configuration before getting into implementation. And this is one of the major benefits of successive refinement. When you're simulating just the logical configuration, obviously any errors that you run into have nothing to do with the implementation details because they're not present yet. And so that simplifies the debugging of the configuration level simulation. Similarly, if you've already verified the architecture, then when you verify the implementation details, you don't need to worry that much about the architecture. Any errors are very likely to be part of, or to be coming from the implementation details. So suffice to say that successive refinement is a methodology that has been built into UPF. It was developed by ARM and is being used extensively by ARM going forward. They are delivering all of their IP with constraint UPF so that users can plug into this methodology. And ultimately, this methodology increases the communication between the IP vendor and the user. It enables separation of the logical design from the implementation, and that simplifies verification and debugging, and also allows verification to start earlier in the process when you only have the configuration details available and haven't yet finished the implementation. This methodology overall provides an organized approach to developing power intent for IP-based designs that helps ensure compliance with the requirements for that IP, as well as enabling better and more and earlier verification of the IP and the system containing that IP. In particular, it allows for clearer communication between the IP provider and the consumer of the IP, and ensures that you can separate the logical design from the implementation of that logical design for the power intent. And that enables the verification to start earlier when you just have the configuration information, and also to proceed more quickly because you can debug separately the configuration of the logical control of the power management from the implementation details. As a result, you can start verification earlier and you can complete verification more quickly and do a more thorough job of verification in the flow.